Hi everyone, in this video we are going to cover direct syscalls in practice, the technique that allows bypass userland, antivirus and EDR hooks by calling the Windows kernel directly, skipping the entire API chain. We will go from the theory of how the Windows system mechanism works through manual implementation using WinDbg, automated stuff generation with SysWhispers3, integration into a Havoc C2 beacon. We will close with a live evasion against both Microsoft Defender and Bitdefender. This is Christian Ramirez from RBT Security, and we love teaching and mentoring the next generation of cybersecurity professionals. Make sure to subscribe and hit the bell button so you get notified when we upload new demos. And guys, if you're helping us grow, we will be able to make more videos, so you can easily helping us by liking the video and share it with your team, your security community, or anyone who wants to go deeper into offensive development, or even in your social media. It really does helping us continue creating more demos every week and keep us more consistent. So let's get into it. Our agenda for today's demonstration is divided in four different phases. So we are going to start with the syscall architecture, understanding the normal Windows call chain and exactly where antivirus and EDR products hook into it. Then we go hands-on. So in section 2 is the portion of the demo. We will have three different demos. The first one is going to be manually implementing syscall technique by extracting the syscall number using WinDbg, by reading the ntdll, disassembling, then automating the whole process using SysWhispers3. Finally, we are going to integrate it into a Havoc C2 beacon. The last two sections, 3 and 4, so it's going to be the result and how we are going to show how Defender was bypassed and evade, and explain precisely why Bitdefender's runtime detection still fires. So two different detection layers, two different outcomes. Let's move on. So let's start with the Syscall architecture recap. So before to go to the demo, so let's align on the mechanisms. So when our code calls any API call, it doesn't jump straight to the kernel. It changes through the layers. The first layer is going to be the kernel32.dll. The second one is the kernel base.dll, and the third one is the ntdll.dll. Finally is where the all the stuff they're going to be. So those ntdll stuff contain the actual syscall instruction. So that is precisely where the antivirus and EDR's products place inline hooks. They override the first bytes of the stuff with the E9 jump instruction. So basically this instruction and redirect through the inspection engine before allowing the real kernel transition to proceed. So the key diagnostic that allows us to identify is if a stuff starts with E9 instead of the expected B8 for the instruction move EAX, that function is hooked. Direct syscalls is the technique that allows us to bypass the entire implementation of the antivirus and EDR hooks by implementing our own stuff. So the antivirus and EDR hooks in the ntdll they will never reach. So for that reason, it's a technique that allows to bypass the way how antivirus and EDR's API hooks work. Let's move on to the next slide. So in this one, we have an example of the direct syscall using the NT allocate virtual memory. So as you can see on the left side, so we have our implant, right? This one. So as you can see, and we have our four instructions that we need. So the move instruction, both of them. The first one is the move R10 to RCX. right? Preserve the first argument per the 64 calling convention. The move EAX to the SSN loads the syscall service number that tells the kernel which function to execute. And then the syscall fires the transition from the ring 3 to the ring 0, or the kernel mode, right? So basically the entire normal API chain is like this. So once we execute our implant, our malware, the malware goes to the Windows API in kernel 32, and after the kernel base, and after the inside the ntdll, right? So but instead to do that, using direct syscalls, what we are going to do is go directly to here, right? So every EDR hooks in those layers, right? Inside of the either kernel 32 or ntdll. The most commonly is an ntdll, right? But with this technique is completely skipped. So basically, and as we can see in here on the right side and the kernel mode, so we have the key system called 64, which receive the call via the L star MSR and the SSDT, which resolve the syscall service number to the actual function pointer. So for example, in here we have this SN 18, which maps to the empty allocate virtual memory, right? And the kernel routine execute and returns, right? So now it's time for the demo. So for this demonstration, as I mentioned, we are going to have three different implants. The first one, we are going to show how manually can be created. The second one, we are going to use SysWhispers3. And finally, we are going to integrate the beacon, the Havoc beacon, and we are going to show the modifications that we did to be able to evade Microsoft Defender statically and dynamically. And also, we are going to show how Bitdefender react against this technique. Right? For this demonstration, we are going to use three different virtual machines. Right? Let's jump to our first virtual machine. So in here we have our first virtual machine. So, and we have our codes. So in here, this is the bare minimum information that we need to have. We are going to go over the three documents, but one of the first mandatory requirements is that we need to identify this number, so the SS number. So, and we can do it two different ways. The first one we are going to do it manually, and we are going to hard code the value. So one thing that I want to mention in here is that in every single Windows operation version, that number is different, right? So we are going to open any executable. We are going to use Notepad, and we can do this. Let me just actually adjust. There you go. Let me adjust the font to make it bigger. That way you can see it. Okay, perfect. So in here, we mentioned on the previous slide, we need to go inside this DLL, ntdll.dll. So, and since we already have it loaded, so the first thing that we are going to do is to disassemble and get the number that we need. So we are going to use this command, and as you can see in here, so this is the number that we need, right? Basically, we are disassembling the ntdll virtual memory Win API. So, and basically this is the number that we need. So we have to add it in here. In my case, for this version of my operation system that I am using it, I already have it, which is 18H, right? So the second one, we just need to copy and paste and go back to WinDbg. And basically we just need to replace this command. And as you can see in here, so we got the number, which is 3AH, which I already have it, 3AH. I am just showing this to you guys just to in case that you want to follow along. And the next one, the value is 3AH. Oh my bad. So actually is this one. The next one is nt create thread. Let me update it and the code in here. Let me go back in here and just put it again. So as you can see, we got the number, which is 0C2H, which perfectly match, right? And finally, we are going to get the nt wait for signal object. We replace it, and as you can see in here, is the number 4, and we replace it. As you can see in here, this is basically our stuff, right, that we need to have because we are going to link them to our main program, our implant. So another file that we need is our headers. So basically in here is we need to come up with the prototype, our wrappers, that every single NT NT API. So basically, all of this you can get it from internet. So and then in here we just need to populate it. So we have the nt allocate virtual memory, we have our nt write virtual memory, we have our create thread ex and wait for signal object, and we have our main program. So and as you can see, we have the most common headers, right? But we have to integrate our sys functions header, which is this one with the prototypes, what we call our wrappers, right? So, and in here is I create the global function. And basically this global function is, I call it inject shellcode. So basically, so we are going to call our NT Windows API calls. So in this one, we are calling the NT allocate virtual memory, right? So if everything goes well, it's going to go to the next one. If something goes wrong, it's going to print a message. But basically in here is we are allocating the new buffer, right? So and in here we are making it executable, readable, and writable. Of course, this is not a good implementation, but this is just for showing for the demonstration. So next, everything goes well, is going to go to write the shellcode, our payload, and we are using nt write virtual memory, right? And if everything goes well, so we are going to create the new thread, which we are using the nt create thread with all the parameters, right? And finally, so we are going to wait for the execution, right? With the wait for signal object, right? That basically is going to wait till the thread is died. So, and in here we have our main function, right? Inside of our main function, we have our shellcode. That basically this is a calculator shellcode. So nothing fancy. And inside of our main function, we are just calling our global function that we created in here, just to spawn our calculator. So one thing that I want to mention for this demonstration, Microsoft Defender is completely off, right? And the next step is to proceed to compile it. So here we are going to compile it. And once it's compiled, we have our main. Um, okay. And as you can see in here, the calculator just pop up, right? So, and basically what we did in here, just we are using direct syscalls. And just to demonstrate that our implant is using our NT APIs. So we have these values, right? So for example, if we try to compile it again and we change the value, so we are going to see that this time is not going to work, right? So, and the reason why is because this value is wrong, right? So that is why it's very important that we use WinDbg or any other debugger to get the SS numbers. Okay, so let's put it back. And let's proceed with the second demo. The second demo, as I mentioned, we are going to use SysWhispers3. So let's open it, the files, and this is open syscall.h, and we need one more, which is syscalls asm.asm. Okay, so this is the command that we are going to use to generate these three files. I didn't create any of these three codes, so it was automatically generated using the SysWhispers, and that we just with this command. So we can execute it just to see how it looks. We can just open a new terminal here, and we can just here copy this path, and here yeah, it's a demo one. So we can go to demo 2. Demo 2, my demo 2. Okay. And in here we have the SysWhispers3, but what we are going to do is we are going to create a new folder, sys test, and we are going to just copy these three files and put it in here, and we are going to copy our Python script, and we are going to put it inside of here, paste, and let's go inside. And now we are going to use this command, we are going to see that it was generated our syscall.eh. That basically is this file, our syscall.c, which is this file, and our syscall asm.asm, which is this file. So these three files, and we don't need to do anything about it. So in here, what we need to do is to create our own implant, right? So basically in here, let me go over very fast to the code. So we are defined this NT success, right? We are going to use it later on in the software and in our implant. So and in here is basically is pretty much the same global function that we used in the previous sample. So is I call it inject shellcode, and basically we are calling the nt allocate virtual memory, the nt write virtual memory, the create thread, and finally is using calling the nt wait for signal object. One thing that I want to point out is that all SysWhispers append this SW3 pretty much in every single Win NT API. So it's something that is going to matter. So we are going to see why later on. So and in here we have our main function. So again we are using the same calculator payload, and basically in here we are just calling you, right? Uh, our our global function in here, right? So now it's time to compile it. Let's demo 2. Let's compile it. And we are calling this time implant. And we have our implant in here. So, and again, for this demo, we still have Microsoft Defender completely disabled. So we are going to execute it. And as you can see in here, our calculator just pop up also. But the main difference is that the implementation of SysWhispers, and basically in here we left on the debug option. So basically we can see when our implant is finding the opt call for the syscall, right? So which is good. And then in here it just we inject our shellcode, and we got the calculator pop-up, right? Which is it's fine, right? So now is I'm going to proceed or transit to the next demo. For this one, I'm going to start enabling Microsoft Defender, right? Okay, except the automatic sample submissions. So the rest will be fine. So in here, we already have our implant, right? If we try to execute it again, we will see the Microsoft Defender complaint. And basically, and didn't allow us to execute it. And eventually, it's going to eliminate our implant and put it in quarantine. Okay, from here, we are going to basically in here, we just cover the manual implementation right here, and we also cover the automation when using SysWhispers3. And now we are going to transit to the evasion and, the integration of our Havoc C2 Bitcoin, and show the modification that we did to be able to evade Microsoft Defender, and also partially the Bitdefender. So we come back in here, And what we are going to do is move to our other directory. Okay, in here we have this one. Right. For this one we have this main. Okay, let me open the other one. Whisper C, SysWhisper H, and also SysWhispers assembly. Okay, so and in here the main differentiators that we did to be able to evade Microsoft Defender is that if you recall, in our main implant, so what we did, it was just to first we integrate an IS decryption. So we encrypt and we integrate a decryption function, global function for us to decrypt it and runtime. So our payload is not in clear text anymore. So we also and integrate our IBs, right? So and along with our payload, and as you can see, our payload is very big. So that was one of the first modification that we did. So I'm here. So basically, we just declare a few constants, right? So it is the size of our encryption key, that is 32 bits, which is this one, and also we are declaring our IB size, which is 16, which is part of our payload itself, right? And in here we just declare our syscall pointers, right? And here we are using our ntallocate virtual memory, ntprotect virtual memory, ntwrite virtual memory, ntcreate thread ex, and the wait for signal object. And in this one, and I decide to do not use the nt wait for signal object. Instead, and I decide to create another function called resolve APIs, and we are using get model handle and get proc address to get in runtime execution pointer to the address of this wait for signal object, right? And basically in here we can say that we are using 99% of direct syscalls, and the other percent, and we are using regular Windows API, which lives on the user LAN, the wait for signal object. And the reason why is because wait for signal object API is very widely used with different programs and is not flagged by any antivirus or EDR by itself. It gets flagged when an antivirus or EDR hooks they see wait for signal object along with, for example, create thread ex, right? That combination and trigger the alert. So, and in here, basically, it's pretty much the same. We have our main function and pretty much the same, right? So we are calling our global function, right? To decrypt. If everything goes well, we start calling our ntallocate virtual memory, our write virtual memory. In this case, we use the ntprotect virtual memory, right, to change the protection from readable to executable and readable. And again, we use the create thread ex. And finally, we are using the wait for signal object. So that was the first change that we did and our main implant. So the next change that we did was we switch the R11 CPU register to R15. If we go back to the one that SysWhispers use, they're using job R11, which is highly monitored by Microsoft Defender. So we change it, right? Another change that we did is we modify this SW3 because SysWhispers append these three letters. So, and also is highly monitored by Microsoft Defender. We just remove it and we rename it. Every single NT API that we are using it. So, and we did pretty much in every single file, right? So, and basically with those small changes, we were able to evade Microsoft Defender. So now the moment of the demo. So we are going to compile this one. One thing that I want to mention is, and again showing again, is Microsoft Defender is fully enabled. So we are going to compile it, and we are going to also execute this command, right? And our name of our implant is called cloud. So we are going to see that cloud, we're going to use process hacker, and we are going to also show the Microsoft Defender still right in here. We are going to execute it. And one thing in here that I didn't show you is I add a breakpoint. Actually, it's not a breakpoint. I just add a get chart. So basically, we are interrupting the execution until we press a key of our keyboard. And that one is going to be used for the demonstration against Bitdefender. But for now, if we go back in here and we check here, so once I press enter, so you can see our process still in here, still running, and Microsoft Defender is not complaining. If we go back to our Havoc, we can see that we got the beacon, right? And we are going to execute commands just to show that our beacon is fully functionable. Let's just execute this command, and let's just wait till the beacon check in. In the meantime, as you can see in here, nothing happened. Microsoft Defender hasn't been able to detect anything. So in this one, I think is for the previous test that I did, right? So we can even see those ones if we want. But let's go back to Havoc, and as you can see in here, we were able to get the output of our two commands. The first one was the ipconfig, and after that we execute the buff bell, right? Yeah, basically, and yeah, we got all the information. And as you can see in here, Defender hasn't been able to detect enough, no complaints on anything, right? All right, so having said that, so now the next step, I'm going to kill this our implant, because the next step that we are going to do is to show this under a debugger, just to see how is it looks under the hood. So I'm going to disable it again, and what we are going to do is in here as we are going to relaunch our cloud.exe, and it's going to get pause, right? So it's going to get pause in here, right? So we are going to use 64 DBG. We are going to fire up, and we are going to go to File. We are going to click and attach. We are going to attach the process. Oh, sorry, I did not touch the right one. Okay, where is it? Let me do it again. Attach this one. Okay. So, and in here, basically what we are going to do is we are going to go to symbols. We are going to go to the ntdll.dll. And basically what we are going to do is we are going to just copy the name of our NT APIs. So we identified in here. So what we are going to do is we are going to put a breakpoint. We are going to emulate yeah, I can say that we are going to emulate antivirus or EDR API hooking, and we are going to see if our implant go and hit those NT APIs. So this one, as a matter of fact, I really believe that they have it. Okay, I already have it. I think I was a part of the previous test that I did. So even I added the one from the Userland, the equivalents, virtual alloc, virtual protect, create thread, and wait for signal object. Right? A few of them they're disabled. Let's enable. Let's enable it. Okay. So now we are going to go to the CPU, and it says running in here. But what we are going to do is press enter or return in my case, and we are going to see on the debugger that we hit our first breakpoint, right? So in this is something expected because as I mentioned, we are using the kernel 32 for wait for signal object, right? And in here, so the next breakpoint will land in our ntdll, our syscalls allocate virtual memory. And in here you can see we can determine that Microsoft Defender do not use any API hooking, right? So because we don't see our indirect jump instruction, we are seeing regular and conventional assembly instructions, right? But in here, if we just follow the execution, we are going to see that our syscall was called and we hit our first syscall and we press and run. We are going to see that now we hit the second one that is inside the ntdll nt protect virtual memory. We can see it in here. So with this, we are proving that our implant is using our syscalls, right? Our NT APIs. And again, so we can just go and press step over, and in here, so we are showing that right, that everything is working as expected, right? So just click it and again press run. So and again, so we hit the NT protect virtual memory, so which is inside the ntdll, which is something expected again, right? And this one, it hits a lot of times and use a lot of times the NT virtual protect memory. So what I did was disable this one just to pass forward faster. Otherwise, we are going to spend a lot of time in here. And again, it go back to allocate virtual memory, right? Allocate virtual memory. So we are going to disable also this one, since we already proof that we are using the syscalls. So and in here, so if we go back to our Havoc, we see that we go a second beacon, right? So our second beacon is in here, IP. We are going to execute the IP config. So and one thing that I want to mention, once we get our Havoc beacon, so and if you recall, we also create put a breakpoint to the conventional Windows API and the userland. So, and right now we hit the breakpoint inside the virtual protect, but this is after that we go our initial session, right? So in this one, if we disable it, so we go back in here and we run. So we are going to see that our beacon is the next time that check-in is going to get our the output of the IP config command. So if we go back in here and open it, and so they still running, right? And the communication is still there. So all right, and we just got the output, which in here we prove that our implant is using direct syscalls, right? And yep, so let's move on to the next machine where we have Bitdefender, and we are going to see how Bitdefender behave with our implant. So let's terminate this. Let's go back in here. Let's finish this. Let's move on. And okay, it says whispers. Okay, let's move on to the directory. The demo 3 Havoc evasion. And in here we have our cloud in here, right? So we are going to use Python server, right? So the next thing where we have Bitdefender. Okay, and in here, as you can see, and let's just wait till the machine completely booted up properly. In the meantime, we go in here. So we are in this section and evasion, and this two results. We show the reason why Microsoft Defender was unable to detecting us and blocking us. Now we move on to Bitdefender. So in here in Bitdefender, and we were able to bypass or evade the static engine. Was clean, so Bitdefender didn't detect us, but Bitdefender was able to detect us on a runtime execution. So specifically at the time when we hit or start executing the direct syscalls, we are going to see that under the hood, exactly how it looks using a debugger. And yeah, so let's jump back to our Bitdefender machine. As you can see here is the icon of Bitdefender, right? So for those that are very familiar uh, with Bitdefender, you can see that Bitdefender add this check mark, and when it's in green, that means that it's clean, right? So, but we are going to use one browser, and so we are going to okay, if I'm not mistaken, this is the right IP. Let me check. No, 192.168. Okay, let me go back to and here is port 8000. Port 8000. Okay, the IP. Let me check the IP here. IP config is 192.168. 180.80. Okay, the IP is wrong. Okay. Oops. What is going on here? Oh my Jesus Lord, what is happening? HTTP. Oh, okay, I see the mistake. My bad. Guys, sorry. And here's okay. So in here we can see all the data. So we are going to download the cloud.exe, and I want to show that Bitdefender is completely enabled. So let's enable it. Let's enable everything. So make sure that everything is enabled, and we are going to re-download it again. The protection, the antivirus is enabled. Right, let's go back. Let's go to advanced threat defense. The advanced threat defense is enabled. Everything, there is no exceptions. Right, there is no exception than anything. Right, so let's go back. I'm going to re-download this file one more time, and we go in here. We can see that Bitdefender didn't complain. So we are going to copy this file. We are going to put it inside of just for convenience users. Let me see here. See users, when users. Yeah, actually I already have it here. I'm going to replace it. Yeah, replace. Okay. We are going to use a PowerShell, and we have it in here. So the first thing that we are going to do is we are going to execute it, and we will see how Bitdefender react. And after that, we are going to use a debugger, and we are going to see how exactly it looks like. Right. So cloud. Okay. And in here, I just executed. If you recall, so we add a get chart on purpose to kind of like a pause the execution. As you can see, Bitdefender hasn't complained. At this point, I just want to point out that we were able to bypass or evade the Bitdefender on this engine, right? Nothing suspicious. So even Bitdefender allowed us to execute it. But as soon as we hit enter, you will see how Bitdefender react, right? So right away they react, and it says disinfecting in progress, right? They detect it, and the reason why is because direct syscalls is an old technique, right? And in these days, modern antivirus and EDRs, they know how to detect that pattern, right? So as a next step, what we are going to do is to analyze it, right? So we are going to analyze it, as you can see here, more details. And what we are going to do to be able to analyze it, so we will have to go to the protection. We are going to, let's open, let's open the calculator. Which one is nt-allocate, 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 nt-allocate virtual memory. Okay, and if we go in here, we can see that this nt API call is not being hooked by Bitdefender, right? But if we go to the next one, nt-allocate, is this one actually, nt-protect virtual memory, nt-protect virtual memory. nt protect virtual memory. This one is not hooked either. Let's move on to the next one. The next one is nt create thread. nt create thread. nt create. Oh, it's not typing. Forget. Okay, system breakpoint reach. Okay, let's do it again. Let's just kill it. Okay, let's relaunch it again. Open. Call. Got symbols. nt create. Create thread, which is this one. Now we can see the Bitdefender hook this Win API, right? So, and here we know that, right? So Bitdefender is just hooking this NT API. So and that is the reason why is detecting that we are using direct syscalls. So and it looks like is also this one is supposed to be hooked. Let me see, nt write virtual memory. I put it a comment. nt write virtual memory. nt write virtual memory. nt write virtual memory. Let's go and see. Oh yeah, is we also Bitdefender hooks this nt write virtual memory. In summary, so we are using for our implant allocate nt allocate virtual memory, nt write virtual memory, nt protect virtual memory, and create thread, and we are using 4. So Bitdefender hook 2 out of 4, right? Because this one is no syscall, is a conventional Windows API. So in here, right? So once that is the reason why when the Bitdefender detect that we are using jumping and we are not using the conventional API change, so is detecting it, right? So remember that the conventional and API change, it says that we have to go from here when we execute it to the kernel 32DLL, after the kernel base, and after the ntdll. And from the ntdll, we have to jump to the kernel mode. But since we are doing something completely different from here, we are jumping to here. So that is the reason why Bitdefender is detecting us. So now if we go back to Bitdefender in here, what we are going to do is now that we saw that Bitdefender is hooking these two NT APIs, what we are going to do is we are going to go back in here, advanced address protection, and we are doing this only for demonstration purposes. So we intentionally we are disable this because I want to show you that the advanced threat protection is the option that I use Bitdefender to hook our Windows APIs, and we are going to analyze how it looks inside the debugger without this option. We already know that Bitdefender counts on a runtime execution, so but it's just for us to analyze it. So I'm going to re-download. Actually, I already have in here. Just let's copy. Um, put it in here. Okay, it looks like okay, still let's put it inside a new folder. Let's see if that allows us. Okay, so we are going to open a new terminal, the new, and in here we are going to execute it, and we are going to execute it. We are going to fire up our x64 DBG. We are going to go file, attach, and cloud, and in here we are going to go again symbols. We are going to go to the ntdll, and what we are going to do is we are going to set a few breakpoints, and let's put a few breakpoints. So let's again, let's see if they allow me to copy, or we have to write everything manually. Copy allocate virtual memory, allocate virtual memory. Let's see. No, allocate virtual. Let's type it. allocate virtual memory, which is this one. So let's add a breakpoint. The next one is write virtual memory. write virtual memory. So this one I already have a breakpoint. So, and actually, yeah, I already have those breakpoints already. Enable. So I guess that is from my previous test. So basically we have the four that we need. Allocate virtual memory, integrate virtual memory, protect, and create thread. So in here, let's go back in here to our CPU window, and we are going to press return. And as you can see, as soon as we press return, we hit our breakpoint. In this case, is inside the ntdll, which is the allocate virtual memory, which perfectly match and is expected, right? But one thing, and that this one is not allocate virtual memory. Yes, allocate virtual memory is not supposed to be hooked by Defender. Is the next one, write virtual memory. If we hit again run protect virtual memory, yeah, right, no, we are going to disable this one to pass forward faster. And now we got and in here and the protect virtual memory, and protect virtual memory. Let's protect virtual memory. Okay, this one actually, let's disable it. Okay, this one, and create thread is enabled. Okay, perfect. So let's continue, and we can see that they're running, right? And here they're running. So let's open in here, and here I'm going to see cloud. Okay, they're running. So, and if we go back and our beacon, in our Havoc, so we will see that we got another beacon in here, and that is because we completely disabled the Bitdefender API calls. The API hook, sorry, and we don't see any. And we go to the breakpoint, and the one that is supposed to be hooked in here is not hooked anymore. The write the create thread. The create thread is the one that is supposed to be hooked, right? And also the write virtual memory. The write virtual memory, is not hooked anymore, right? In here. So, and we did that intentionally just to show you and how it looks under the hood against a Bitdefender and why Bitdefender is able to detect us, stop us, and kill the process, right? And then we go back in here, and basically we see that is fully functional our beacon, right? So yeah, let's go back to our presentation. So basically we finished the three demos, right? And basically in here is our next slide is basically the steps that we use that I already explained, right? So we install the SysWhispers, we run the SysWhispers Python script, right? We review the general stuff, right? So we add to the Visual Studio, we compile it via command line, we replace the calls. Remember that we have to rename and eliminate or delete the SW3 if we want to play around with the Microsoft Defender. We compile and build the implant. We integrate with Havoc, so we integrate we encrypted our payload. We use ICE, right? So and yeah, so we rename all the variables and everything from the SysWhispers, right? And we tested, right, against Bitdefender and also against Microsoft Defender, right? So we already saw all these the results. Let's move on to the next slide. The EDR evasion results. So basically in here, so what we saw is that against Microsoft Defender, all the three metrics are green, right? The static scan, the binary came back completely clean, no signature match. And when we executed Microsoft Defender, real-time protection never fired any alert against the Havoc session, right? So completely we are able to evade Microsoft Defender, and this is something expected. Microsoft Defender is not a good antivirus, right? But in 2026, Microsoft Defender is still not be able to identify the direct syscalls, right? And the reason why is because they do not use API hooking line, right? So yeah, and against Bitdefender, we saw that the static is a different story. The same, we were able to on this on this scan was clean, so we were able to evade Bitdefender on this engine. So, but when we executed Bitdefender behavioral engine, terminate the process before the C2 session could establish, right? Um, and we went inside of under the debugger and we determinate the reason why we got caught, and it's because Bitdefender and identified that we were using the direct syscalls technique. Right, let's move on. So finally, the next steps, right? So and one thing, yeah, that I want to mention is that Bitdefender also use kernel telemetry, right? And what will be the next steps, I guess, to be able to evade Bitdefender? So we have to integrate more techniques. So maybe replace the direct syscalls with indirect syscalls. Maybe integrate call stack spoofing, ETW patching, and sleep mask. And that can be a more robust strategy. The next upcoming section, we are going to see if all these three techniques combined they're able to evade Bitdefender. And but for now, and this everything for the video. Thank you very much, and see you to the next one.